Thanks so much for choosing my workshop. I hope you find it interesting. Before we get properly started, there should be a poll. Miles, have we got that poll? Yeah, there we go. Enlarging an object by a scale factor greater than 1 always results in a larger image. Just a true or false question. I'll leave that open for a bit, and then we'll get started in just a moment. And then I'll hide my video and get started. Interesting results. Okay. So I'm just going to hide my video, I think, so that you can just see the screen more clearly. Right, here's how this workshop is going to look. First, I want to briefly explain why I want to talk about principles and procedures, and I'll illustrate a little bit about what I mean by those. At this point, I won't always use examples from geometry, but that's just a sort of brief overview at the beginning. And then we'll move on. We'll spend the bulk of the workshop looking at transformations. We'll have a very brief look at trigonometry, and then finally some thoughts on perimeter, area, volume, that kind of thing. I hope it will prove quite practical with some easy to take away ideas for you if you like the sound of any of them. So, what's the point of this workshop? Well, have a look at this slide. Here are some things that I've heard from students, and these are all things that would make me want to pull my hair out if I had any hair left. They're all things I've heard like more than one time. The one at the bottom, I mean, that really gets me when I've given students quadratic equations to solve, but they've already been factorized, and they're just so conditioned to expanding that they do that unthinkingly and then realize, oh, I could have just seen the solution straight away. This one at the top here, if you have two sides in an angle, you need the sine rule. Most recently, I heard something along those lines from an A-level student who I happen to tutor, who's from a grammar school. Now, I went part-time a few years ago for various reasons, and a year later, I started to do a little bit of tutoring at weekends. And I mention this because doing this one-to-one tutoring has been a huge eye-opener for me. It's made me recalibrate what I think is possible to achieve with students over a short period of time. But mainly, the one-to-one nature really gives you the chance to dig in to see what students are thinking in a way that I could never do in a classroom. And what I found with this particular student who said this to me was that he was working with some kind of mental flowchart. He had this in his head to help him decide when he was going to use the sine rule and when he was going to use the cosine rule. And this really baffled me. It baffled me because he actually knew the formulas perfectly well, and he was totally unaware that you could just look at a formula and see from the formula what information you needed and how you could use that to work out something. So he genuinely seemed surprised when I told him, look, with this cosine rule, to work out this side length A, if you've got the other two sides B and C, you've got those lengths, and this angle opposite your other side, angle A, that's all you need. And I mean, it sounds crazy the way I'm explaining it, but I could really dig into what this young man was thinking, and he just never twigged. Now, this isn't an issue particular to trigonometry. It's something that he seemed to have missed to do with formulas in general. So yeah, that's why he was relying on painstakingly racking his brains to work on this mental flowchart whenever he needed it. So just a couple of other thoughts on why I want to sort of talk about principles and procedures. And we've got this idea here of when a formula becomes a definition. So just a couple of thoughts on formulas. Often, if you ask a student to give a definition of the mean, they'll give you an explanation of how to work it out. They'll say something like, oh, you add up the values and divide by how many there are, something along those lines. And if a student says that to me, I will usually say, you've given me an excellent explanation of how to work it out, but you haven't really told me what the mean is. On a similar note, if you ask for a definition of gradient or slope for any international listeners, you'll get answers along the lines of rise over run or change in y over change in x, that kind of thing. Now, I suppose you could define the gradient in terms of one of these formulas and then show that a consequence of the formula would be that we can say a line with gradient m will rise by m units for every 1 unit you go to the right. But I actually prefer the latter as a definition. I prefer using that wordy definition and then obtaining one of these formulas as a consequence of the definition, rather than the other way around. Why? I mean, why do I prefer that? Well, to my mind, no matter how much you try to illuminate and justify a formula when teaching it, some students will only internalize the formula itself and nothing else. It's sort of natural. Sometimes when they've been given a formula, they think, oh yeah, I can do these questions now, and they unintentionally switch off from being interested in anything else. So initially, I like to avoid giving formulas and instead give them definitions and force them to work with those definitions so they can think hard about the consequences of those. Of course, I will give them the formula eventually, but certainly not at first. Consider this problem here. If you follow me on Twitter, you might well have seen this before, but I'll just give you a few seconds to read it. So here we've got some points. They lie on a straight line with equation y equals 2x plus c. A student that understands gradient can work out these missing values in seconds. They can do it in their heads. They see we've got a gradient of 2, so they know that that means every time you go 1 across, like we are from P to Q, that you must be going 2 up. So they can see that this is going to be 9.238. But compare that with a student who is just heavily reliant on the formula and doesn't really have much more of a conception of gradient. Well, they're going to be relying on this formula, they're going to be substituting in these nasty decimals, and they'll make a right meal of it. I mean, they might still get the right answer, but it'll be a whole lot more work. So that's just a couple of thoughts on formulas. Let's just have a look at this here. Here's a fairly standard simultaneous equations question with a typical type of student response. That should all be correct there. Now, from experience, I know it's quite possible to find a student who can competently do all of this that you can see on the left of your screen, but who would then be thrown by this problem here on the right. Just give you a moment to read that. So the students that can do the problem on the left, but seem a bit confused by the one on the right, they're likely to have internalized a procedure, the procedure you see on the left, but they've missed a key underlying principle, possibly because they've spent long periods of time practicing the elimination procedure, doing loads of questions, but not really thinking about what's happening. Now, to my mind, the question on the right is the easier one. It's just a case of substitution. There's no solving required. So if a student is a bit flummoxed by that one, it's probably because they only learned the procedure that you see on the left. They didn't maybe even see that you could check your solutions by substituting them both into both equations and making sure that both equations are satisfied. But this is a really key idea. It's a hugely important principle when it comes to solving equations, whether it's just a simple linear equation or a quadratic equation or simultaneous equations. The point is the solutions satisfy the equation. And I know lots of students might be comfortable with that when it comes to the simpler equations, but somehow when you start layering on all these procedures, they kind of lose sight of that basic bit of understanding sometimes. And this just becomes something so complicated, they just have to keep focusing on the procedure. Just one more before we launch into transformations. Just another thought on methods. Here we've got a question that I've actually used with lots of groups of Year 5 students in the past. And what I want to show here is that methods don't necessarily encapsulate key understanding of ideas. So I've been surprised with the number of students I see who attempt this question, but do it with 3 separate calculations. So it's quite common to see students doing what you've got on the left of your screen there. They do 3 separate calculations. Of course, the answer to this can be worked out with just the 1 calculation. But like I say, only about half of the year 5s that I've taught have done, would have spotted the shortcut straight off the bat. Now, of course, I do want students to be competent at performing column addition and subtraction, what have you. But more broadly, I want them to have understood the nature of addition and subtraction years beforehand, years before they're worrying about decimals and things like that. So if they've really understood that, they're going to see the more efficient option for themselves, or at least a higher proportion of them really ought to my mind. So here, it's not that I'm concerned about their competence with column subtraction, but also that they can really see, this is what's going on, maybe visualize a number line or have some other mental model that makes them appreciate that that calculation on the right is going to get you the same answer, the correct answer. So those are just some thoughts about how I've seen principles sometimes being lost in the midst of procedures. I hope that makes some kind of sense. But now let's sort of dive into the transformations, which hopefully we'll find some interesting thoughts here. So this is the main part of this workshop. You can see roughly where we are at the bottom of your screen. Hopefully, if it's not too blurry, we've got transformations, trig to come, and mensuration at the end. Now, here are a couple of wrong ideas that some students get in their heads. I'll be looking at ways that I've considered to address these in the next few minutes. So the first kind of wrong idea students sometimes get is that you can only transform 2D shapes. Now, for this workshop, let's just assume I'm only talking about transformations in 2 dimensions. I'm not doing anything fancy in 3D, but even if we restrict ourselves to 2D transformations, it is a misconception to think transformations only apply to 2D shapes. And again, this is something I've got just from talking to students one-to-one and getting them to articulate exactly what they're thinking. And the second type of wrong idea, as you see on there, is that students either mix up a specific mathematical definition with an everyday English definition, or maybe even a technical definition from some other subject. So I'll come back to that a little bit later. Here's an idea then that we could start with, which I think can work well for certain students. So we're going to be looking at, instead of going straight into transforming some kind of polygon, which is where most textbook exercises start, why don't we start with transforming a single point? So here we've got translation. What does it look like to translate just this point here, just A? We can demonstrate that, we can talk about the vector, and then we can move on. We can say, all right, can we translate 2 points at the same time? Well, yes, we can. We can talk a little about that. Then we can move on to translating lots of points that happen to lie on the same line. And you'll see where I'm going with this in a moment, but yes, we can. This is what it looks like to translate lots of points that lie on the same line. Next, we can consider translating a line segment. Now, the key idea here is that when you're translating a line segment, what you're really doing is translating infinitely many points at the same time. We have got infinitely many points, and we are translating all of them. Fortunately, we don't have to think about translating each of these infinitely many points individually. We can just translate the 2 endpoints and then join them up with a ruler. Now, this seems really, really obvious to us, but it's quite a fundamental idea. And the thing is, not a lot of students appreciate that this is actually the case. So what I think I would be doing is, particularly for some students, is really articulating what's going on here. And the idea that we're not just translating vertices. That's quite a common thing that I hear from students. Not just with translation, actually, with any transformation. They just think, oh yeah, I apply it to the vertices. which is true. That's how you would go about the method, and then you could join them up. But they sometimes think that the transformation somehow doesn't apply to any other points on the object. Okay, let's move on to enlargement, or dilation for sort of any international listeners. I actually prefer the term dilation, to be honest. I think it carries the same baggage as the word enlargement does. I'll explain what I mean by baggage later, but it does have some advantages. Anyway, I'm going to use enlargement for now on because, you know, I'm in England and this is where I work. So often the topic of enlargement, and to be honest, this is how I've done it for years, and I'm not very happy about it, but this is what I've done. I'd introduce it in stages, and first we'd see scale factors greater than 1. Then maybe I would consider scale factors between 0 and 1. And then after that, we'd look at negative scale factors. And I might break that down into sort of 2 parts. We'd have sort of scale factors between 0 and -1, and then scale factors below -1. But I've got a minor concern with this and a bigger concern as well. The minor concern is neglecting looking at scale factor 1 and scale factor 0. Fortunately, actually, that's not been a real issue for a while because I do normally address this explicitly. I'll use GeoGebra or something like that and specifically talk about what does it mean if we enlarge by scale factor 0? What does it mean if we enlarge by scale factor 1? And we look at that. The bigger concern is this. It's that students don't appreciate that enlargement, no matter the scale factor, is always really the same thing. They start to see enlargement as 3 or 4 slightly different procedures. Not completely different, but still too different for my liking. And what I want is for them to really appreciate that the procedure is exactly the same in all cases. So the poll results, I'm afraid that was a bit of a trick question. I think we had 94%, unless I'm mistaken, who went for true. Enlarging an object by scale factor 1 always makes the object larger. Now, I'm going to say that's not actually true, because I could be talking about a point. I deliberately used the word object. I didn't say, you know, polygon or some kind of 2D shape. And I'll come back to that in a moment, but let me just talk about something else. I want to talk about the use of the word and how mathematical words can sometimes confuse, especially when you've got an everyday English understanding. So mathematical idea, it almost kind of fits in with everyday English, but students have to accept a couple of slightly weird things. First, they need to accept that mathematical enlargement encompasses the idea of making things smaller as well as larger. But they also need to accept the idea of negative scale factors, which lead to the 180-degree rotation you kind of get when you do enlargement with negative scale factors. So there's a bit of weirdness. You know, enlargement in maths does not mean exactly the same thing as enlargement in everyday English. And there's a couple more subtle differences that we'll look at in a moment. Let me ask you a question. Which of these is the more fruitful way, do you think, of seeing enlargement? Do we like to think of enlargement as a transformation applied to an object, or a transformation applied to the distance between an object and the center of enlargement? Now, mathematically, I actually prefer the first one. I think it's just correct to say the mathematical transformation enlargement, we can apply it to objects, whether it's a point, whether it's a line, whether it's a polygon or anything else. But for students, there's this idea of actually this sort of clicks into place a bit more if we talk about enlargement as something that's being done to distances. And I'll try and illustrate that here. So we're going to revisit that idea I had earlier on about just focusing on a point rather than a polygon, because typical exercises, they will always start with, you know, some kind of triangle or flag shape or rectangle, whatever, that we're going to be enlarging. Why do that? Why not just start with a point? So we can mathematically enlarge this point A to obtain its image like this, right? I'm using a scale factor of 3, by the way, so that is the enlargement of A. In terms of everyday English, the point hasn't got larger. It's just a point. It has no dimension. So that's why the correct answer to the poll question is false. Enlargement by a scale factor of something greater than 1 doesn't always enlarge an object if the object I'm talking about is just a point. You might call me being a bit sneaky, and perhaps that's true, but hopefully you see why I'm getting at, why I did it. But this also illustrates the baggage with the word enlargement. Students, when they translate or reflect a point in a very sort of real everyday English sense, you are sort of translating, you're moving that point along or reflecting that point. Whereas with enlargement, when you enlarge a point, it doesn't get larger. What is effectively happening is that this vector is being changed. So scale factor 3 means that this vector here to the image is 3 times the original vector that we had. Now, by thinking in terms of vectors, we can see that the procedure is exactly the same, whether we use a scale factor of 3 like this, or we use a scale factor of 0.5, or a scale factor of -2. We are just multiplying this vector by the scale factor. And by doing this, I hope to help students appreciate that enlargement is just one procedure. It's one and the same. We don't have to think of, oh, when it's scale factor greater than 1, I'm making the shape bigger. And then if it's a bit less than 1, but greater than 0, I'm making the shape smaller, and all of this. And have to have these different sort of slightly separate models in mind. Okay, so we've had a look at a point, enlarging a point. Let's get rid of that and go back to scale factor 3. Let's contrast enlarging a point with enlarging a line segment. So here we've got a line segment. Now, when I enlarge the line segment, that does indeed get longer. So this kind of matches our everyday English understanding a little bit more than enlarging a point does, right? Enlargement really does seem to make this longer. But now let's look at a line instead of a line segment. So this is an infinite line, and when we enlarge it, we end up with another infinite line. So mathematically, we can enlarge it. Both have infinite length. So in everyday English terms, it doesn't seem right to say that by enlarging it, we've got a longer line now. So again, this might be another way of thinking about that poll question. Does enlarging a line make it larger when we've got a scale factor greater than 1? We do multiply it by 3, but does it actually get longer? Okay, so hopefully I've made clear what I'm trying to communicate here. Just a point about language. While we're talking about language, here's another thought. Reflection is another one that seems to carry the baggage of its meaning in everyday English. One of the cool things in maths is that objects can be on both sides of a mirror at the same time, which isn't true in real life. I mean, I suppose you can say that's true if you think of reflection as sort of in terms of folding a bit of paper. You can have that mental model there. But with a real mirror, you can't be on both sides of it at the same time. Whereas in the world of maths, you can be. Anyway, reflection is one of those things that students look at in science lessons. And recently, a student asked me some really quite interesting questions that I hadn't considered before. So I put this applet together. So hopefully you can see a triangle, and it's being reflected in the line, and we've got its image over here on the right, and nothing controversial there, I hope. That is a correct reflection. Now, what if instead of a line of reflection, I just had a line segment? I had a finite mirror. Does this still make sense? Is this a correct reflection? I'll give you a moment to think for yourselves. Is this a correct reflection? Okay, hopefully you've had a chance to think. Now, I'm going to say that actually we can't reflect this object in this mirror, at least not mathematically, because when we do reflection, we need to sort of look at perpendicular distances. So we pick a point on the object and see how far it is away from the mirror in a sort of perpendicular direction. And there is no mirror here, so we can't do this reflection. So mathematically, we can't do that. But what about if we had a person down here? In the real world, or in a physics lesson, a person located somewhere around here, let's say there, would be able to see this reflection in this mirror, even though it's only a finite mirror. The mirror does not extend up here. And it's just one of those things. The mathematical location of the enlargement is correct, but it kind of relies on us having an infinite mirror. But in the real world, we don't need an infinite mirror. We just need a suitably located observer. So why am I bringing this up, really, to be honest? Because it's not something that comes up in a maths exam. Well, I only mention it because I'm a huge fan of cross-curricular links. In the classroom, I'd always feel like I'm a teacher first and a maths teacher second. And also, I think it's just one of those things that when you show it to students, they quite often appreciate it. They think it's quite interesting, and they do appreciate the link with their other subject. Okay, moving on. Let's do that. Earlier in the week, I tweeted this question out here. The idea being to come up with reasons why each of those 4 transformations could be considered the odd one out. So hopefully you're familiar with the idea of which one doesn't belong. The point is not to find the odd one out, it's to come up with a reason why any one of those could be the odd one out. And there were a few amusing responses, like enlargement's the only one that doesn't end in "tion," like reflection, rotation, and so on. Turned into Sean Connery there for a moment. But a handful of people engaged with this seriously, and had some really, really interesting responses. They involved things like this. So there was a bit of debate about orientation, but to my mind, orientation is talking about the order of vertices in a sort of clockwise or anti-clockwise direction. So only reflection changes the orientation of a shape. So here we've got ABC, if you can see my mouse, going sort of anti-clockwise, whereas the images of A, B, and C are going in a clockwise direction. So reflection changes orientation, but none of the other transformations there do. There was also a nice point about inverse transformations, in particular how a reflection is self-inverse, and that's generally not true for translations or enlargements or rotations. I mean, it's only true for 180-degree rotations, but not others. There were quite a few responses involving matrices, which we'll briefly look at in a couple of minutes. But there was a really good one actually from at Robot Maths, Adam there. A really, really nice response actually about how it's possible to represent a translation in 2D using a matrix, but it really relies on a 3x3 matrix. It's something I hadn't considered before. If you're interested in matrices, that kind of thing, do check out that thread, because I found it quite neat actually. And there were also some replies about congruence and similarity, with the claims that rotation, translation, reflection, these top 3, always give you a congruent shape, whereas enlargement won't always do that. With enlargement, you'll get a similar shape, but it won't always be congruent. You'll make it larger or smaller. But this is only true if we make a particular assumption. What I'm saying is that actually rotation, translation, and reflection don't always give you a congruent image. In particular, it's reflection that doesn't always give you a congruent image. And someone called Katie did actually spot this, which was quite pleasing to see actually. And I'm going to demonstrate that here. Reflection only gives us a congruent image if we reflect in a straight line. But what if we reflect in a curve? So we're going to do this activity together, and then at the end I'll explain why I think this activity has some value. But anyway, this activity is something that's really easy to set up to do with students. All you really need is plain paper, pencil, ruler, pair of compasses. And what we want to do here is reflect a line. So this is the line I'm actually interested in, so just ignore that point. I want to reflect this straight line in this semicircular mirror. Now I want to stress that, you know, for those who are aware of such things, this is not some kind of Pamgaea disk, there's no hyperbolic geometry involved. I'm just trying to use some key stage 3 knowledge of reflections with one other key fact. And I'll mention that key fact in a moment. But this is just, can we do this with key stage 3 students? Can we get them to think about how this line would look when reflected in a semicircular mirror? And I'm going to give you a moment. Actually, can you try and visualize what that reflection of that line is going to look like? I'll give you a few seconds to have a think. Okay, let's see. What I'm going to do is hide the line so we can just focus on a particular point. Let's say we've got the point there. The extra fact that your typical key stage 3 student would need to know is how to find the perpendicular distance from a point to the circumference. And what I would tell them is what you need to do is position your ruler so it joins the point and the center of this circle or semicircle. So they would have their line, I'd say just pick any point, so they might pick that point on the line, and then position their ruler so it joins to the center of the circle. And then what I'd want them to do is measure the distance there, and then measure the same distance on the other side and mark that point. Okay, and then we could just repeat that process with a few different points. We'll pick a different point on the line, measure it with a ruler, mark the point down there, pick a different point, measure it, mark it, and in not too long, you can have a student who has marked, you know, maybe 20 or 30 points along this line. I wonder if this is matching your sort of mental image that you had when I asked you to see if you could predict what this would look like. Now, luckily I've got GeoGebra here so I can mark all of the points continuously, so I've got trace on, and the reflection of this line looks like this. Well, at least this segment of the line gives you that. It will go off to infinity, but that's kind of what we got. I wonder how many of you predicted that. Maybe some of you did. I certainly didn't when I started it. I think I was carrying some baggage myself from being aware of hyperbolic geometry. I was thinking about circles and that kind of thing. So anyway, what is the point of this activity? Why do I think this has any value whatsoever? Well, firstly, it's fun and it gets students thinking. I mean, how curious were you when I asked, what do you think this line is going to look like? Secondly, and I think more importantly, this focuses on the perpendicular distances, which is one of the key things that we care about when it comes to reflection. It's the key principle. But thirdly, doing a task like this highlights something that we don't get when we do reflections in straight lines or any of the other transformations. And it's highlighting that transforming a line means transforming every single point on the line. That idea I had earlier when we were looking at translation. Transforming a line means transforming every single point on the line. Now, when you've got straight lines that always get transformed to straight lines by our typical textbook questions, of course, you can just use the shortcut of taking two endpoints or two vertices and joining them up. And you lose this principle that, yeah, as I've said, transforming a line is transforming every single point on the line. And by getting students to actually pick 20 or 30 points on the line and do them one by one, they kind of get drilled into this idea, which I think is sort of a key underlying principle. We're forced into doing this to get a sense of what's going on. Okay, that's enough of that. Right, next. Okay, just before we finish on transformations, I want to look at a quite different way of thinking about transformations. So the most common way, at least at Key Stage 3 and 4, is to think of transformations as acting on objects on a static grid. And that's what I've been doing in all of the previous slides. We've been applying transformations to objects, whether that's a point or a line or some kind of shape. Transformations applying to objects on a static grid. But there is another way to think about transformations, and this way turns out to be really helpful for students who go on to study higher level maths. And this involves thinking about transformations as working on a copy of the whole Cartesian plane. So I will illustrate both ways of thinking using reflection in the x-axis as an example. So in the first way of thinking, we imagine a static background. And what I'm going to do is reflect this blue square here, this unit square, in the x-axis. Now, don't worry about the matrices or anything for now, but just look at what's going on. I have reflected the unit square in the x-axis. Notice what's happened to the coordinates. That point there with coordinate 0, 1 got mapped to 0, negative 1. Okay, let's put that back to its starting position. The other way of thinking about transformations, remember, was thinking about the transformation applying to the whole plane. So that is going to look like this. If you watch carefully as I do this, we're transforming the whole plane like that. Now, if you think about it in this way, in this system, what's neat is that the coordinates remain unchanged. That point there is still 0, 1, which is kind of neat and useful for various things that we don't need to get concerned about right here, but it's a way of thinking. And there's more that's quite neat about this. Let's look at a different transformation, because reflection really isn't really the best way of illustrating this. Ooh, technical. All right. So given the time constraints, I'm not going to go into lots of detail about matrices, and obviously some people will be more familiar with this than others, but we have a matrix here that can transform this particular unit square, and it will do this. It's going to turn it into that. Okay, this is obviously the first way of thinking. I have transformed the unit square on a sort of static background. Now, let's think about that same transformation, but applying to the whole plane. If we do this to the whole plane, what it does is this. And again, we see that the vertices of that unit square have the same coordinates in this new system. They're still 0, 1, 1, 0, and 1, 1, so on. So that's quite neat. But what's even cooler is that if you look at the coordinates, or rather the position vectors, let's say, of those 2 points, let's take the green one. We see that this green one is 2, negative 1. And that perfectly matches this column vector here, the first column of the matrix. And the red one matches the second column of the matrix. Now, this won't be news to any of you who are familiar with matrices at all. So I apologize for that. But lots of you might not be familiar with this kind of thing. Maybe you don't teach sort of further maths at A-level. Lots of people don't. So I'm bringing this up for one main reason. It's really that a sound appreciation of transformations early on is really hugely helpful to students when they encounter linear algebra in sixth form in university much later on. Now, of course, not every student will go on to study more advanced maths, but just having some sense of what is to come can help you sort of think a bit more carefully about the foundations you're laying for those students to build on. Okay, so I did say we'd have a sort of brief look at some trig. Again, if you follow me on Twitter, you've probably seen this before, so apologies for that. but I'll give you a minute to think about how you might answer this one. The responses I had on Twitter were quite interesting, actually. I didn't have many, but the one or two that I did have were quite interesting. Okay, hopefully you've had a chance to think. With this, many students, particularly older students, and even some teachers, they will autopilot their way through this question using the sine rule. But actually, there's no need for the sine rule or even any knowledge of trig ratios. I have seen a year 8 student who's never met trig, like sine, cosine, that kind of thing, get this correct. So first of all, we can easily find the two missing angles. We know angles in a triangle add up to 180. And in both cases, they are 44 degrees. Evidently, these are not drawn to scale. Now, the main idea, the principle I'm talking about for this is that for any given triangle, the larger the angle, the longer the opposite side. The larger the angle, the longer the opposite side for a given triangle. Now, a lot of people intuitively realize this. I feel like I've known this for like most of my life, but I don't think any teacher ever explicitly told this to me. So I had to work that out for myself. And I think most people who are maths teachers probably are in the same boat. We kind of know this, but do we actually explicitly tell this to students? I don't know, but I do know that we do all make a very big deal about a special case of this. We do talk about the hypotenuse being the longest side of a right angle triangle. And of course, the right angle is the biggest angle in there. But that is just a consequence of this sort of underlying principle that the larger the angle, the longer the opposite side. So again, some of you might well have known this already, but I thought it worth including because there was someone, I can't remember who it was, but there was definitely an episode on Craig Barton's fantastic podcast where it was mentioned that this wasn't, you know, they didn't feel that this was common knowledge. So hopefully you see the value in this. It's not just to take a shortcut on a question like this. It's having that sense then makes it possible for students to perform a quick sense check of answers where they do have to use the sine rule or the cosine rule, or maybe make predictions for like an upper or lower bound for an answer based on the information they've got. It's just really valuable. It's a good idea to have in your head and for students to be aware of. Okay, so we're into the last section. We're going to be talking about perimeter, area, and volume. Sorry, I didn't really finish on this, did I? The point is, yeah, sorry. The first triangle being isosceles meant that the x was 10. Those two sides are the same. Whereas in the second triangle, you've got a 10 centimeter side that's opposite a 43-degree angle, and this y centimeter side is opposite a larger angle, so it must be greater than 10, and that means y must be greater than x, because we know x is 10. Sorry, I kind of didn't make that clear earlier on. Right, perimeter, area, and volume. So I'm going to start with this mathematician joke. I won't read it out. I'll let you read it for yourself. Now, I don't think this is a particularly hilarious example from the genre. There are some I really like, but I've included it because the point of this joke is relevant to what I want to communicate in the last sort of 10 minutes. Reducing problems to something that we've previously solved. Before we do that, I just want to return to the theme of formulas. So, yeah, just talking about formulas. Some teachers like giving students a formula up front and then getting them to practice using the formula. For these teachers, understanding where the formula is something that can be developed later. And I'm not saying that's right or wrong. And you know, it's up to you to decide what seems to work for you. But I do have a concern with the approach. I'm really open to hearing other opinions. In fact, I'm going to two sort of polar opposite workshops later today. I'm going to be going to Pete Mattock's and then Chris Bolton's later. So without wanting to speak for them, I imagine they have quite different views on this kind of thing. But my concern with formula first is that once a student learns the formula, it's harder to motivate them to consider where it comes from, why the formula works, because they think, oh yeah, once I've learned the formula, I can answer most questions, at least the typical questions that rely on it. But what if they forget the formula? Like, what if they're just not motivated to learn more, dig into why this formula has come about? Just a thought. Don't take things I'm about to say as gospel. I mean, I don't suppose you would anyway, but really, please don't. Like I say, people will have different views. I'm okay with it. Just all I'm suggesting is that consider what I'm saying and then decide for yourself if it matches, your experiences in your classrooms. So just want to have a look at a few things. We're going to have a look at the area of the circle, area of the trapezium or trapezoid for any North Americans, and just a couple of other things. So if you go straight into area equals pi r squared, I think some students will just see this as a procedure, and it will almost completely, for some students, sever the link with the underlying idea of what area actually is. It just becomes a thing they do, and they almost forget that it's related to even area, even though the word area is probably in the question. So personally, I think there's huge value in activities like this one, where you get students counting squares, which kind of calls back to something they would have done years earlier when they were first being introduced to areas of rectangles in primary school. Now, of course, counting squares will only give us approximate areas for a circle, but that's perfect motivation for needing a formula. Now, in terms of deriving the formula, that's beyond the scope of most young children. Like at the point where we teach them how to find the area of a circle, I wouldn't expect them to be able to rigorously come up with pi. I mean, it's not realistic. But I still think it should be reasonable for students to appreciate that it's sensible. So something like this, sorry, let's just go back. They might not know that, they might not be able to derive pi r squared for themselves, but you want them to be able to see that the area is a bit less than 4r squared by considering sort of this blue square being made up of these 4 squares, each of which has side r. So yeah, area of a circle is just a little bit less than 4r squared. That makes pi r squared seem sensible. Moving on, like I say, area of a trapezium or area of a trapezoid. How might we approach this without giving students a formula up front? Well, going back to that mathematician joke, let's try and reduce the problem to something we already know how to solve. And there are actually lots of ways of doing this. Here are 5 ways. There are actually more than 5. This is not exhaustive. I'll say right now that the 5th way that I'll show you is my favorite, but I'll go through them each very quickly. In the first one, we can consider 2 copies of a trapezium, and they will form a parallelogram. And the idea is that we already know how to find the area of a parallelogram before we come on to trapeziums or trapezia, whichever you prefer. So if you know how to find the area of a parallelogram, you can then see that the formula for the area of a trapezium just falls out of this. Now this is cool, but it's not my favorite because to me it's not immediately obvious that 2 copies of a trapezium will definitely form a parallelogram. I mean, they will, but it's not obvious. It kind of relies on quite a general grasp of alternate angles on parallel lines to realize that you will get actually this sort of perfectly straight edge going on here and a straight side down here as well. So that's why it's not my favorite, but it's still quite neat. Might be worth showing students, it depends. Similarly, same thing with the rectangle. Now, interestingly, again, no one ever justified the formula for the area of a trapezium to me when I was younger, and I never really gave it much thought. But in my head, this is the one that I came up with for myself. I would always just see a trapezium as sort of an average kind of rectangle, take the average of the two parallel side lengths, and you can create this rectangle. But again, I did come up with that for myself, but to be fair, I don't think it's obvious that you will get this perfect rectangle, again, without that sort of understanding of angles on parallel lines. Now this one, I had never seen before until a couple of years ago, but that's quite neat. Area of a triangle being 1/2 times this base times height. But again, I don't think it's obvious. So that's why this isn't my favorite. We've got another sort of parallelogram similar to the first, except this time we're halving the trapezium. Same kind of issue as with the others. Now this last one, to be honest, doesn't even really need the animation. This is my sort of favorite way of looking at this, because it only requires knowledge of area of a triangle, and it doesn't quite require the general understanding of alternate angles. You just need to appreciate parallel and perpendicular lines, and you can see that the area of this triangle down here, this bottom sort of left one, is 1/2 BH, and the area of this triangle up here is 1/2 AH. And yeah, we don't need that sort of general understanding of alternate angles, and students will be able to see the area of a trapezium easily before having to memorize a formula. They can construct this formula easily from themselves. You know, we've got this 1/2 BH plus 1/2 AH, which you can then factorize into the more sort of commonly presented version of the formula, you know, 1/2 H brackets A plus B. So there's some other advantages to starting off with this sort of split into triangles rather than going straight for the formula. Like firstly, it helps students understand where this formula comes from. It's not just something that they're being told to just trust. Secondly, it gives them a fallback method should they forget the formula, if they can at least remember, you know what, I can split a shape up into smaller shapes. And if I know how to find the area of those smaller shapes, I can find the area of the whole shape. At this point as well, I just wanted to shout out a nice activity. Here's one from Miss Constantine. It's on mathshko.com. Yeah, like you can see, there's some trapeziums here. They've been split into triangles. Yeah, just a nice activity. And actually, there's loads of really nice stuff on that website. So yeah, definitely do check it out. And follow her on Twitter as well if you don't already. Loads of good stuff. Okay, just a few minutes left. Again, I'm going to be stating something completely obvious, which will almost seem like an insult, but I'm going to do it because I think it's just not obvious to all students. If you put two-dimensional shapes together, the area of the compound shape is going to be the sum of the areas of the two individual shapes. And that means if you've got a 2D shape that fits inside another, then it must have a smaller area. I mean, like I said, it seems obvious, but it just isn't to all, especially when you contrast it with the idea of perimeters. If you take the perimeters of those two separate shapes there, and then put them together, the perimeter of the compound shape is not the sum of the individual perimeters. So it's one of those key ideas that seems obvious to us, but students don't often pick it up unless they're explicitly told to, or given a chance to discover this. But they still need to be given that chance. And sort of analogous to this, we've got the same sort of issue with 3D objects. If you put two of them together, the volumes of the two individual ones will add up to the volume of the compound object, but the surface areas of each will not add up to the surface area of the compound one. Now, I'm kind of running out of time, so I'm not really going to go into this hook I was going to talk about, but if you're not already a fan of Dave Gorman, do check out Dave Gorman, he's brilliant, but I'm going to have to skip this just so that we finish on time. I'll just sort of end on this one before a summary. Just want to talk about guess what's in my head questions. Now, this is a phrase that Michaela teachers talk about a lot. And basically what they say is, a guess what's in my head question is a question that you know students cannot answer. And lots of teachers, myself included, sort of easily fall into this bad habit where we ask these questions and when the student can't do it, we'll try and cajole them into giving a correct answer by saying things like, oh, that was really close, or that's not quite, maybe you just need to do this. And it's not educationally a good thing. And I agree, by the way, that this is a bad idea. However, I want to suggest that in some cases, it's quite easy to make a subtle change that turns one of these questions into a more reasonable questions. And not only that, I argue it can be a desirable thing to do. For example, suppose you know your students have never encountered surface area before. So asking what's the surface area of this cuboid straight off the bat is a bad idea. But what if you change the question to something like this? What's the area of the net of this cuboid? Or what do you get if you add the areas of the 6 faces? And the thing is, if you've taught them well before this, students should be able to do this and get it all correct. Which then begs the question, do you need to teach surface area? Or is it sufficient to just give a definition of surface area? Now, I know surface area becomes tricky and talking about nets is difficult when you start getting into sort of curvy objects like spheres, but I'd suggest consider giving a definition first. Force them to understand what surface area actually is, and only then start working with these kind of shortcuts at the bottom. I mean, most students for themselves will probably spot that you can pair off opposite sides of a cuboid and sort of take that shortcut there. Not many people will spot the bottom shortcut. I mean, students won't, but obviously as teachers, we can sort of generalize a cuboid to any prism and show that there's another way of working out surface area. If you haven't seen that before, you might sort of quite like that one. Yeah, just sort of in the interest of finishing on time, I'm going to skip volume and just sort of summarize with these points here. So some topics, I think, especially in geometry, they lend themselves to this approach where you start with a key principle or definition, force them to work with that principle, and that might mean you've got to create exercises that are not your typical sort of exercises, and only then start introducing formulas and procedures. So thanks so much for listening. I appreciate there was a lot going on here, but with the virtual conference and sort of not being able to see sort of immediate feedback on people's faces, I thought I better do something quite sort of wide ranging so there's at least something for everyone rather than risking over pitching or under pitching. So yeah, hopefully you enjoyed it. Do let me know what you thought on Twitter. I'm sorry I wasn't able to keep an eye on the chat box during the presentation, but yeah, do let me know. And I hope you really enjoy the rest of your day. Thank you so much.